The whole bar from A to B has the same diameter, 20 millimeters. It's all made of one material, A36 steel. We're in SI units since we have meters up here. We look at A36 steel up here. It has a modulus of rigidity of 75 gigapascals. While we're here, I want to find the yield stress for the material, the shear yield stress for the material. For the A36 steel, we have a normal yield stress of 250 megapascals. So I'm going to estimate my shear yield stress as half of that, 125 megapascals. So we want to just make sure that the maximum shear stress is less than this to make sure that we are still in the elastic region. We're going to need to cut this into 3 sections. So I'll put those up in a second here. We need to cut it here between B and C, where the torsion is going to be constant between B and C. We're going to need to cut it between C and D, where the torque is constant, and between A and D, where the torque is constant. So for each of those sections, I want to know the length of them, since I'll be using them in my calculations. The length between A and D is 0.2 meters. Between B and C is 0.8 meters. And between C and D, 0.6 meters. And we want to know the total angle of twist of point B, which I can also refer to as the twist between A and B, since A does not move and B is free to twist. We need a free body diagram for each of our sections. So as I said before, we're going to need 3 sections for this. It'll take 3 sections such that each section has a constant internal torsion, internal polar moment of inertia J and G. I'm going to take the section between B and C. We have that applied load of 80 Newton meters acting on the edge of it. And remember, how did we decide the direction of torsion? Similar to how we do the direction for our internal normal force. We put our thumb in the direction of where that internal normal force would be, and then with our right hand rule, that's the assumption we're going to make on the direction of that internal torsion. So from the out from the cut, my thumb is in that direction, so my fingers curl in this direction. That's the direction I assume the internal torsion, BC. And for convenience, I'll make that my x-axis. So when I do my sum of moments, I know if it's positive around that x-axis or negative around the x-axis. But again, the direction of the internal torsion only has to do with the outward normal from that cut surface. My second cut, I'm going to cut between C and D and take everything forward. And notice when I'm taking everything forward, I don't have to worry about what's happening at the wall. We're not asked for the reaction at the wall, so this will save us just a little bit of algebra by not including the wall in any of the pictures. Still have that 80 Newton meter, and now I have a 20 Newton meter moment or torque around the other direction. I have internal torque TCD. Then my last cut, cutting between A and D, I'll have that 80 again. I'll have that 20. And now I have my last 30 Newton meter. And that'll be TAD. Before I get to my equilibrium equations, I'm actually going to start by finding, in this case, I just have that one polar moment of inertia. Just so I have it for later, I'm going to calculate its value. They give me the diameter of 20 millimeters. So that way I have it later. The polar moment of inertia for all of the sections, since they have the same cross-section, is going to be 15.7 times 10 to the negative 9th meters to the 4th power. From the equilibrium, in these problems, I only get per free body diagram one equilibrium equation. I'm going to sum moments around the x-axis in each picture. I arbitrarily assigned x to be along this direction. I could have said it was the other direction just as easily. I'll still get the same numbers. This will be a little bit more convenient because of the way I'm drawing my internal torsions. So along the x-axis, I have a positive 80 plus TBC. Which means that TBC is a negative 80 Newton meters. Picture 2, I'll have a positive 80 minus 20 plus TCD. TCD is negative 60. The third picture, I'll have 80 minus 20 plus 30 plus TAD. So TAD is a negative 90. Now I can go to the next step. I need a compatibility equation. So this relates the deformations or the angular deformations of the sections to the angular deformation in my system. I need to know, I'm asked to find what the angular deformation is from A to B. How can I calculate the angular deformation from A to B? So just in general, it's going to be phi AD, plus phi CD plus phi BC. I can now solve for these unknowns using the deformation to internal load equations. So for each of my sections, I can calculate its angle of twist. For each one, I use TL over GJ for that section. In this one, section AD. Here, I already know the value of TAD. I was able to find it as a number was negative 90. I erased it, but I had up there what the length of section AD was 0.2. G is the material property for all of them, 75 gigapascals, or 75 times 10 to the 9th. And the polar moment of inertia was the same for all of them. That was 15.7 times 10 to the negative 9. Again, I'll point out I'm using all base units here. This is in meters to the 4th. This is now in pascals, newtons times meters, and meters. For delta AD, I get negative 15.3 times 10 to the negative 3 radians. Do the same thing for CD. I know that's negative 60 times 0.6 over 75 gigapascals times 15.7 times 10 to the negative 9 meters to the 4th. So the angle of twist in CD, I get negative 30.6 times 10 to the negative 3rd radians. And for BC, I do the same thing. I won't go through all of the details in this one, but negative 54.3 times 10 to the negative third radians. I can use my results from 5, 6, and 7 in my equation 4, and I can get what the total angle of twist is going to be between A and B. I just have to add these three numbers together. I get negative 100, with some rounding here, negative 100 times 10 to the negative 3 radians. So finally, when I'm talking about my angle of twist of that free end, I want to interpret what direction that's actually going to be. Unfortunately, I erased the free body diagram. I'll redraw it quickly here. So this was our first free body diagram. From the way I directed x here, I got an angle of twist of negative 100 times 10 to the negative 3 radians, which is 5.74 degrees. But I want to know around the axis I established, should it be clockwise or counterclockwise? This is where I have to look at what assumption did I make, or what direction is t around the x-axis, and then I can determine, is it going to be in the same direction as t or the opposite direction of t. I have a negative value here, which means that, okay, we have to think about it in reverse. It goes in the opposite direction that t does. So if I have a positive value for phi, then it's going to go against the direction of t. If I have a negative value for phi, it's going to go in the same direction as t. I have a negative value here, so that means that my twisting is going to be around the x-axis counterclockwise. Because in this case, that's not always the case. If they all have the same R, they all have the same J, we only care about which one has the highest value of T. If that's below the yield stress, these must be below the yield stress. In general, though, if you have sections with different J values and different radii, you might have to calculate several shear stresses to make sure that everywhere it is below the yield stress. In this one, though, we only have to worry about the 90 Newton meter one. We have 90 Newton meters times the radius, which was 10 millimeters. Yeah. Divide by the J, which we calculated earlier. So the maximum yield stress, again, it's maximum at the outside radius, so I'm only calculating it there. And I'm only calculating it in section AD, since that had the highest internal torsion. The maximum shear stress for this is going to be 57.3 megapascals. So our last step, verify. We have to verify that our TL over GJ was good to use. The maximum shear stress we saw in the system was 57.3. That has to be below the yield stress, which we said was 100. We estimated at 125. So it is less than the yield stress. So this assumption is valid to use the linear elastic region.